Today I'm going to talk about consistency as a theory, or in short, CAAT. Well, it's a long CAAT with 2 A's. My name is Thomas Haas, and this is joint work with Roland Meyer and Hernan Ponce de Leon. To motivate this talk, let's look at a typical verification problem. Here we have a concurrent program and a specification, and we want to find bugs. How do we find bugs? Well, we might want to use a bounded model checker. How does bounded model checking work? Bounded model checking works by taking the input, using some logical theories, to convert the input into some logical formulas. So we have a formula for the program, we have a formula for the specification, or more precisely, a formula that describes bugs. Then we throw this into an SMT solver. The SMT solver will eventually return and tell us, oh, this is unsat, you don't have bugs. Well, up to a bound. I mean, it's bounded model checking, okay? And if it's sat, we have a real bug. Now, there's a little problem here. This problem is underspecified. Why is that? Because we have these concurrent programs. And to think about concurrency, you need to understand how threads communicate. Well, how do they communicate? Over some shared memory, right? They write into shared memory, they read from shared memory. But to understand that memory, well, you need some notion of a memory model that describes how the memory works. And so to complete this problem here, we just take the memory model also as an input. Then we do the same procedure. We use some logics. We will see what kind of logical theory, and make a formula out of that, throw it into the mix, and now we have a bounded model checking problem that is parametric in the memory model. But this gives rise to 2 questions. Question number 1, what actually are memory models? And question 2, how can I formulate them in theories? So let's start with the first question. What are memory models? Now, here I've brought the most simple example, you know, probably sequential consistency. We have threads, and they communicate directly and atomically with a shared memory. What this means is that if one thread performs some memory operation, let's say a store, this memory operation is immediately visible to the other threads. This is quite easy to understand because this notion of memory coincides with the idea of interleaving semantics. You take the thread instructions and just interleave them. But the problem is real hardware doesn't work like this at all. This would be too slow. So here I've brought a more realistic memory model called total store ordering, or for short, TSO. In this memory model, we have buffers. To be precise, we have store buffers. The threads, when they perform a store operation, first write into this buffer. At some later point in time, these buffers get flushed into the main memory. And only at that point in time, when they are flushed, the other threads can observe these store operations. So you can think of there being a delay between in the communication, okay? And real hardware does work like this. And real hardware does also do a lot of other stuff that makes it more complicated. Now, we want to take these memory models as input to our problem, right? So we need some uniform language to describe these memory models. And fortunately, such a language does exist. And it's called CAAT. So we will describe these memory models using CAATs. Now, what is CAAT? Well, CAAT is a domain-specific language that can be used to describe memory consistency models. You can describe sequential consistency, TSO, but also like ARM and Power. And you can even describe language-level memory models like C11 or the Linux kernel memory model, RC11, release acquire, whatever. You can express everything, basically. How does this language work? Well, it talks about relations. And here I've brought the strongest cat, the tiger, the sequential consistency. And it's quite compact, the syntax, but it talks about relations and compositions of those relations. A few of these relations are so-called base relations. They are not defined in the memory consistency model itself, but they come from the program. For example, here we have PO, RF, and CO. PO stands for the program order, telling us in which order a thread performs its instructions. RF is called the read from order, and it connects load operations to store operations if the load operation obtains its value from that store operation. In a moment, we will see what it looks like. And the CO, you can ignore it for now. Then, from these base relations, we can compute new relations called derived relations using standard operations, union, composition, intersection, and so on. In this case, we have a so-called from-read relation, FR. You don't have to understand what it does. And there's a more interesting relation, HB, which stands for happens before. It tells us which operations happen before another operation. So they give a notion of time. This relation gives a notion of time. And because this relation gives a notion of time, we require it to be acyclic, okay? So we have axioms in this language that tells us, look, this has to be acyclic. Great. Now, to give you another example, here's TSO, or at least a snippet of TSO. And the structure is sort of the same. We are going to define some happens before notion and require it to be acyclic. The difference here is that from the program order, we remove some parts. This allows sort of to model reordering in the instructions. And you can model store buffering like this. I won't go into detail why this is store buffering, but this describes store buffering, okay? And which might be quite interesting because we don't even need to talk about buffers at all and still can model store buffering. Okay, so let's look at an example. Here I've brought Peterson's mutual exclusion algorithm, at least a snippet thereof. And it works like this. We have two threads, and first they store into some shared variable that they want to enter a critical section. Because both of them may want to enter the critical section at the same time, we need another way to distinguish or to give someone priority. And for this, we use a turn variable t. And the idea is the threads are not egoistic. They are cooperative, so they pass the priority to each other. And then there's a loop in which they simply wait as long as the other thread wants to enter the critical section and it's not their turn. Or in other words, they can enter the critical section if either they get the turn passed or the other one does not even want to enter, then they can also go ahead, okay? And now we want to check if this algorithm has bugs. And well, now this depends on the memory model. Let's observe an execution. So first, we rearrange the code a little bit, get rid of the signatures and the globals, make some space. And now we want to define one single execution as an example. First, we need the program order. But as I said before, it just tells you in which order the instructions are getting executed per thread. Next, we need a read from order that tells us where do the load operations get their values from. On the left thread, you can see that we are also allowed to read the initial value of the memory, which we designate by this init instruction, okay? And if you look closely, the left thread actually reads the value 0 for G, compares it to 1, so the comparison fails, which means it will leave the while loop early, so the second check does not even get executed. Okay, lastly, we need the coherence order, and now I can tell you a little bit more about what it means. The coherence order is a total order on stores of the same address. Why is that? We can have multiple concurrent stores, but the memory has just one cell, so to speak, one value of this location, right? So the memory has to decide in which order these stores are getting committed into the main memory. What is the last value that is going to be there? And in this case, we have that the second thread performs its store first, or it reaches memory first, and the first thread, its store reaches second, okay? And now the question is, if you look at this execution, we see, first of all, this is a buggy execution because the first thread can leave its while loop and enter the critical section, right? Because it reads the value 0, it thinks the other one does not want to enter the critical section. And the second thread, well, it observes that the first thread wants to enter the critical section, but it also observes that it got a priority pass to. So it thinks, well, I just go ahead and also leave the loop, okay? So this is a buggy execution. The question is now, can this actually happen? So first we look at sequential consistency. Now, what we need to do is just evaluate the relations defined by the consistency model. First, we have the FR relation from read, and it looks like this. We just take the read from relation, turn it around, then move coherence forward. So maybe I can point it here. You see? These highlighted edges give rise to the from read edge. Now, all of these edges are happens before edges. So these vertical bars in the definitions are unions. Yeah, okay? So everything happens before. Now we need to check if there are cycles. And indeed, there is a cycle. And because there is a happens before cycle, this execution is not sequentially consistent. It cannot happen under this memory model. So there's no bug. At least this execution does not expose the bug. How about TSO? Well, we start from the same execution. We again compute from read, the same way we did before. It's identical. But now we need to change the program order a little bit. We need to remove store to load orderings. This is what the memory model tells us. So we get rid of 2 edges here. And again, the remaining ones are happens before edges, all of them. And now we are looking for cycles again. And if you look closely, you don't see any cycle. There are no happens before cycles. And because of this, this execution is actually consistent with total store ordering, which means Peterson has bugs under TSO. Okay, so this algorithm would not work under total store ordering. Okay, now we've seen how to look at one single execution and evaluate if it's consistent or not. But the problem is we want to look at all executions, right? We need to verify that all of them are bug-free. And for this, we want to exploit the SMT solver or a SAT solver that does the search for us, the exploration. So we need to encode CAAT into logical theories. And CAAT has quite simple operations, right? Union, intersection, and so on. And since we're working over a finite domain, I mean, we have a bounded program, we're doing bounded model checking, you can encode all of this just in plain SAT. It's easy. There are also axioms. We've seen the acyclicity axiom, but there are 2 other ones, emptiness and irreflexivity. And again, emptiness and irreflexivity are easy to encode in plain SAT. For acyclicity, you have to think a little bit harder, but if you go to the world of SMT, you can use first order theories, and in this case, you can use so-called integer difference logic to get a straightforward encoding. I won't show it, but it's quite easy. So what's the problem? Why don't we do it just like this? Well, CAAT actually allows you to define recursive relations. So, for example, the transitive closure. And recursive relations, well, they have a least fixed point semantics, and existing theories don't really have a good time capturing least fixed point semantics. I mean, first order logic in general has a problem with capturing least fixed points. And here comes our contribution. The idea now is, to give you an example, okay, first the idea, we don't encode CAAT into a logical theory, but we see it as a logical theory itself. To give you an example, here's TSO again. I've divided it into 3 parts, the base relations, the derived relations, and the axioms. And what we're going to do now is, we look at the base relations and define a theory over those base relations that says what interpretations of the base relations are consistent with the theory, and we blend out all the derived relation stuff and the axioms. Those are going to be hidden inside the theory. So the theory will only talk about the base relations, but it will evaluate if the base relations are consistent or not using the derived relations and axioms. To give you a more concrete example, here is a sentence in the theory of TSO. Let's say we have events instructions A, B, and C. A and B are in program order, B and C are in coherence order, and C and A are in read from order. This would be a cycle. Under SC, this would already be a cycle and would not be allowed. For TSO, you need a little bit more. You also need to know that C and A are in different threads, which is shown by the external relation here, ext. And you need to know that A is a read operation. And if you know all this, then you will get a happens before cycle. And because this would be a happens before cycle, it's not allowed. And because it's not allowed, the negation of this thing is a sentence in the theory of TSO. Okay? To be a little bit more general, we don't do just TSO. We take any CAAT model for the and can see it as a theory. On the other hand, we can also be a little bit more general in the base relations. I mean, I talked about memory consistency, where you have notions like program order and read from, and coherence. But you may talk about transactional memory or databases, where you maybe have some notion of, let's say, a transaction relation. So you can also think about database consistency, for example. But for the rest of the talk, we will just do memory consistency. Okay, now that we have a theory, we also need a decision procedure for this theory. In particular, we will start with a theory solver. And the theory solver will take a conjunction as input that somehow describes the base relations. It will do the derivation process we've seen before, perform a check of the axioms. And if the check fails, it will provide an explanation of why. What's the reason that this execution is inconsistent? Why do we, now you may be wondering, why just a conjunction as input? And why do we need explanations? Well, because we put it into a lazy SMT scheme. That means we have, in front of that, we have a SAT solver that takes a general formula psi as input. It will compute a model of this formula, model of psi. And this model, you can think of it as a conjunction by just conjoining all the literals in this model into one big formula. And it passes that to the theory solver. The theory solver will then check if it's consistent with this theory we have. And if not, it will return an explanation to the SAT solver. And then the SAT solver will find a new model. And this goes on and on until you're done. So let's look at the theory solver in more detail. The 4 highlighted edges I've shown here. So how does it work? First, we get this formula phi as input. From that, we extract the base relations. It somehow describes the interpretations of the base relations. Then we do a bottom-up derivation process. Bottom-up because we think of the base relations as being at the bottom and the axioms as being on the top. Then we do a check. We check the axioms if they're satisfied or not. And if not, this is what is the new part here, we do an explanation. But in this explanation process, we go backwards, a top-down explanation. So we slowly get rid of the axiom. We find a violation of the axiom and propagate it downwards. This propagation goes through all the derived relations, eventually reaches just the base relations, and outputs an explanation. This explanation is just in terms of the base relations. Let's look at it. Let's look at an example. First, here we have this graph we've seen before. You may be wondering, why is there a graph and no formula? I mean, it's a theory solver working on formulas, right? Well, if you label the instructions here, you can see this is equivalent to a formula where you just conjoin all the edges of this graph. So we can see a formula simply as a graph and the graph as a formula by just looking at all the edges in isolation. So we will just work over the graph, it's easier. Now, first we do the derivation. We've seen this before. We compute from read. Then we compute happens before. Then we are going into the check phase. We are looking for cycles in this case. We find the cycle, great. So up to this point, we've seen this, right? Now we go into the explanation phase because there's an inconsistency here. We have a cycle. And we just break down the derivation we've done now, but in a backwards manner. First, we get rid of happens before, and we see that the cycle actually consists of program order edges, coherence edges, and one from read edge. But from read was also derived, so we also break this one down further. And this gives us the following subgraph. Now, this subgraph explains why the full graph had a problem, why it had a cycle. And on the level of formulas, you can think about this as a sub-formula of the original formula, an unsub core, if you want. And this core explains why there was a problem. And in particular, because this is a problem, we know that the negation of that is a sentence in the theory of SC. And exactly this negation is what we give back to the SAT solver. So the SAT solver gets an explanation now, and it will simply generate a new model, and this procedure repeats. Okay. So let's come to the evaluation of this procedure. So we have a bounded model checker called D'Artagnan. It's a memory model parametric bounded model checker. The text is input the program as well as a description of the memory model in form of the CAAT. It creates an encoding, so it generates these formulas. And in its initial version, it tries to encode the full CAAT model in standard theories, the whole derivation process, the checking of axioms, and so on. Now with our new theory, we can change this a little bit using consistency as a theory. We move the CAAT into the SMT solver as a theory, and D'Artagnan only needs to generate the constraints for the base relations only. All the other part is now part of the theory, all the other reasoning. And then we made some evaluations. So on simple CAATs, those that involve no recursion, okay, to be fair, I have not talked about recursion here, but I will come back to that in a moment. In memory models that do not involve recursion, you can see that consistency as a theory is not really that much faster than just doing the standard encoding. It's marginally faster, a little bit, because it is more clever in handling acyclicity than standard theories. So for simple CAATs, we don't get much. But then there are memory models that involve linear recursion, transitive closures essentially. And for those memory models, you see more difference. Okay, this is a logarithmic scale with factor 10, so just a little bit difference is quite a lot actually. On the right-hand side, you see the average. And here you can see differences from factor 2 to up to factor 20 in performance. So that's quite nice already. But then there are also very complex CAATs that involve nonlinear recursion, like the power memory model. And here the difference is substantial. So we can see differences of up to a factor of 100. So to conclude this talk, the idea we had was to see consistency as a family of theories. So each consistency model gives rise to a different theory, but they are uniformly described in the same language. These consistency theories can handle fixed points. Well, I've not talked about fixed points, but the idea is pretty much identical to what I've shown you, just that in the derivation process, you need to do clean iteration. You need to evaluate your derived relations multiple times, but this is everything that changes basically. And in the explanation process, you need to reverse this multiple times. But the idea is still the same. Then we've given a general theory solver for consistency theories, and we integrated this theory solver, consistency as a theory, into bounded model checking, and saw that it gives substantial performance improvements. And yes, that's my talk. Thank you very much for listening.
Okay, very good. Time for questions over there.
Okay, thank you for the nice talk. So can we do parameterized verification?
Parameterized verification?
Yeah, with
we have only done it in the context of bounded model checking now, so
okay.
we cannot do infinite.
So related to that, that will be a very hard problem because even first-order logic cannot capture transitive closure, and
Right.
you have that. So your logic will be more expressive than first-order logic. So things will be hard there, I guess.
Yeah.
Is that right?
I mean, it's not strictly more powerful. There are restrictions. Okay.
Yeah.
I've not talked about, but
you're working on this problem yourself.
Sorry.
You are working on this problem yourself.
Yes.
Okay, very good.
Yes.
So unbounded, we don't do unbounded things. No parameterized verification.
Yeah. Okay. So another question, like, see, with bounded, we only can prove like the presence of bugs.
Yes.
So if we want to prove the correctness of programs, can we do some over approximation and maybe use CAATs?
I'm not too sure on that. Maybe yes, but I think you need some sort of interpolation maybe.
Yeah,
we haven't thought too much into that. So for now, our first goal was bounded verification. So it's quite limited in that sense.
Okay. Thank you.
Okay, very good. We have a question over there. on the far left. Yeah, sure. We have time. Everyone is finishing early, so that's great. We have lots of time for questions.
I think we need to give credits for Sumit for running up and down the stairs here. So this is awesome. So this is really interesting. I'm curious specifically about this this theory solver. It looks a lot like a theory for directed graphs, which we've seen before. So there's a quite popular project called Monosat that deals with the theory of directed graphs, among a few other things. And I'm curious if you thought about like the relationship with this between, say, a more general graph theory, and if you had considered what like an encoding into something like Monosat would look like. Okay.
Yeah, I'm not too sure about graph theories, but I can tell you precisely what this theory, where this theory belongs. You can categorize it as a subset of data log, actually. I mean, the derivation rules we have are essentially data log rules, but restricted to binary relations and also unary relations. And this allows for some more efficient handling than general data log. So it's sort of a well-chosen fragment that you can handle quite nicely in a SMT setting.
Okay, thanks.
Okay, other questions? The audience.
I mean, I can also add one more thing if there are no more questions.
Yeah.
So some people might think that bounded model checking is quite limited, but like in practice, people are fine with bounded model checking. So we actually collaborate with industry here. And to give you maybe the nicest example is that we found bugs in the Linux kernel, particularly the QSpin lock. We found it to be broken, which is the core spin lock algorithm in the Linux kernel. But, well, you might be wondering if it's broken. Okay, it violates mutual exclusion and has a deadlock. So in that sense, it's completely broken. But only with respect to the Linux kernel memory model. So as soon as you compile this code to ARM or Power or TSO, you actually don't find any bugs anymore. And we can show this using this parametric memory model system, which is quite interesting. And it led to the fact that now the Linux kernel memory model gets also reworked. So the memory model is more broken than actually the benchmark or the QSpin model.
Very good. Let's have another round of applause. Thanks so much.